Hello students, this is physics question paper 2023, set 2, 55 2 by 2. Set 1 already discussed and I'll put the link in the description box. So as you know, total 35 questions, 5 sections. First section MCQs, section B 19 to 25 short answer questions, 2 marks each. Section C contain 26 to 30. Again, these are also short answer questions, but 3 marks each. 31 to 33, long answer, 5 marks each. And there were 2 case-based study questions, 34 and 35. Okay, let's start from section A. Question number 1. Okay, the ratio of the magnitude of the electric field and the magnetic field in the plane electromagnetic wave. We know that E naught upon B naught is equal to C. So the ratio of the electric to the magnetic field is C. Next is specify the transition of the electron in the wavelength of the line in Bohr model of hydrogen atom, which gives rise to the spectral line of the highest wavelength. For the highest wavelength, the gap should be minimum. Okay, this is n is equal to 3 to 1. N is equal to 3 to 2. This gap is minimum as compared to the others. 4 to 2, 4 to 1. So the gap is less, the wavelength will be highest. So the correct option is n is equal to 3 to n is equal to 2. That is B option. Next is, which of the following will be same for the reflected and refracted rays? Okay, in case of refraction, whenever a ray of light passes from one transparent to another transparent medium, speed changes, wavelength changes, but the frequency remains the same. So for reflected and refracted waves, the quantity which remains the same is frequency, that is C option is correct. Next is the formation of depletion region in the PN junction is due to diffusion of both electrons and holes. Question number 5, an isolated point charge particle produces an electric field 3 meters away. The distance of the point at which the electric field is E by 4. Okay, we know that the electric field due to a point charge is kq upon r square, where k is constant of proportionality 1 upon 4 pi epsilon naught. So when the electric field is E, the distance is 3 meters away. So electric field is inversely proportional to r square. Let us write down E. The distance is 3 meters. E is inversely proportional to 9. Okay, now the electric field is E by 4. You have to find out the distance. Let the distance is r dash. So E by 4, 1 upon r dash square. This is equation number 1. This is equation number 2. Let us divide these two equations. E upon E by 4. Left hand side will be E divided by E by 4, which is equal to 4. And the right hand side 1 upon 9 upon 1 upon r dash square. That is, this will be equal to r dash square upon 9. Hence, r dash square is equal to 9 into 4, 36. So r dash will be equal to 6 meters. Hence, the correct option is D, that is 6 meters. Question number 6. The curve of binding energy per nucleon as a function of atomic mass number has a sharp peak for helium nucleus. This implies that the helium nucleus is more stable nucleus than its neighbors. Next question, question number 7. Current 8 milliamperes flows through a wire. The number of electrons passing through the cross section in 10 seconds. Okay, we know that I is equal to NE upon T. So here you have to find out I. Rest all quantities are given. Current is 8 milliamperes, that is 8 into 10 raised to the power minus 3 amperes is equal to N you have to determine, and E is 1.6 into 10 raised to the power minus 19 coulomb in 10 seconds. Okay, so on simplifying it, you get N is equal to 5 into 10 raised to the power 17. So the number of electrons will be 5 into 10 raised power 17. Next is, which one of the following elements will require the highest energy to take out an electron from them? This will be carbon, because this is in the second orbit. Its electrons are in the second orbit. So the electrostatic force is maximum. Next is, a conductor of 10 ohms is connected to 6-volt ideal source. The power supplied by the source, we know that power is equal to V square upon R. V here is 6, 36 upon 10, that is 3.6 watt. So the C option is correct. Next is, in an extrinsic semiconductor, the number density of the holes is given, the number density of the intrinsic charge carriers are given. And here you have to find out the number density of electrons. We know that Ni square is equal to Ne into Nh. So the number density of the electrons will be equal to number density of the intrinsic charge carrier square of it upon the number density of the holes. Okay, Ni is 1.2 into 10 raised to the power 15. Ni square will be 1.2 into 1.2 into 10 raised to the power 30. Upon Nh is 4 into 10 raised to the power 20. Okay, on simplifying it, you get the answer to be 3.6 into 10 raised to the power 9 per meter cube. So C option is correct. Next question, which is question number 11. Okay, in question number 11, you have to find out the internal resistance in terms of the EMF and the terminal potential difference. Okay, we know that EMF is the maximum potential difference when the circuit is open, that is when no current flows through the circuit. So the internal resistance in terms of E and V and R is E minus V upon V into R. So D option is correct. Next is, a photon of wavelength 663 nanometer is incident on a metal surface. Work function is given. We have to find out the maximum kinetic energy. According to the Einstein's photoelectric equation, maximum kinetic energy is equal to h nu minus the work function. Okay, W naught is the work function. Here nu is not given, instead lambda is given. So nu can be written as hc by lambda minus the work function. Here h is the Planck's constant. Its value is given on the first page, which is 6.63 into 10 raised to the power minus 34. C here is the speed of light, 3 into 10 raised to the power 8 upon 663 nanometer. Lambda is 663 nanometer. That is 663 into 10 raised to the power minus 9 meter. And work function is given as 1.5 electron volt. Okay, this is in SI units, that is in joules. So work function also will convert it in joules. 1.5 into 1.6 into 10 raised to the power minus 19. Okay, very simple calculation. 6.63 upon 63. This will be 10 raised to the power minus 2 into 3 into, simplify it, minus 1.5. You get it to be 6 into 10 raised to the power minus 20 joules. So B option is correct. Next question, question number 13. Beam of electrons and protons move parallel to each other in the same direction. Okay, let the electrons are moving in this direction. This is the direction of the motion of the electrons. We know that the conventional direction of current due to the flow of electrons is opposite to it. So the conventional direction of current will be I1 towards left. Okay, and protons are moving parallel to the electrons. So this is the direction of the motion of the protons, and the direction of the current due to the motion of the protons is in this direction. Now I1 and I2 are in the opposite direction. So two parallel current carrying wires, current flowing in the opposite direction, they repel each other. Okay, let me rub this. Next question. A ray of light, wavelength is given 600 nanometers, propagates from air to medium. If the wavelength in the medium becomes 400 nanometers, you have to find out the refractive index. So here we know that the refractive index is equal to C upon V2. Okay, the first medium is air. So the speed of the light will be C and V2. And C we know is equal to nu lambda in air. V2 is the speed of the light in the medium, nu into lambda in medium. Okay, the frequency does not change. Whenever the ray of light moves from one medium to another, frequency does not change. So the refractive index is equal to lambda in air, which is given as 600 nanometer upon lambda in medium is 400 nanometers. So this is equal to 1.5. B option is correct. Next is a long wire of radius A carries a steady current I. The current is uniformly distributed across the cross section. The ratio of the magnetic field V1 and V2 at a distance 2A. Let's draw the figure. Okay, this is a wire whose radius of the cross-sectional area is A. Now B1 is the magnetic field at a distance A by 2. So let this distance is A by 2. So at this point, the magnetic field is B1 and B2 is the magnetic field at a distance 2A. So 2A will at this distance. So this point will be outside the wire. Here the magnetic field is B2. Now here you have to find out the ratio of B1 is to B2. First, let's find out B2. We know that the magnetic field outside a current carrying wire is equal to mu naught I upon 2 pi r. 2 pi, what is r over here? From the center to this distance, this is 2a. So B1 is equal to mu naught I upon 4 pi a. Now let's find out, this is B2. B2 is equal to mu naught I upon 4 pi a outside the wire. Now let's find out B1 at a distance a by 2 from the center of the wire. Okay, using Ampere circuital law, we know that B1 into 2 pi r, here r is how much? A by 2, will be equal to mu naught into, now the current will not be the same. Current reduces as we go inside. Or you can say that from the center as we go to the surface, the current increases. So let the current flowing through this much cross-sectional area, I dash is, let it through this much cross-sectional area, A by 2, let it is I dash. So first let's find out I dash. How to find out I dash? The current is I for how much cross-sectional area? For pi into A square. Okay, for pi into A by 2 whole square, the current, let it is I dash. So simplifying these two, that is dividing these two, what do we get? I dash is equal to I by 4. Okay, now B1 into 2 pi, what is R over here? A by 2. Mu naught I dash is I by 4. So B1 is also equal to mu naught I upon 4 pi A. So what is the ratio of B1 is to B2? It is mu naught I upon 4 pi A divided by mu naught I upon 4 pi A. It is 1. So the correct option is 1. Next 3 questions are assertion reasoning questions. So the first part is work done in moving a charge around a closed path in an electric field is always 0. So this is true. Electrostatic force is a conservative force. This is also true. Okay, here the reason is the correct explanation of assertion. So the correct option is A. Okay, conservative forces are those due to which the work done in a closed path is equal to 0. Question number 17. In Young's double slit experiment, all the fringes are of equal width. Absolutely correct. The fringe width depends upon wavelength, capital D and small d. We know that the fringe width, which we represented by beta, beta is equal to lambda capital D upon small d. So this is also correct. Fringe width is depending upon these three factors. Okay, and the reason is the correct explanation of the assertion. So the option is A. Next is diamagnetic substances exhibit magnetism. True. Diamagnetic materials do not have permanent dipole moment. This is also true, but the reason is not the correct explanation of assertion. Hence, the option is B. Next question. Section B. Each question is of 2 marks. Given that the separation between the two slits is small d and the distance of the screen from the slits, that is capital D, is 1000 d. If the first minima falls at a distance small d from the central maxima. Okay, we know that the distance of the first minima from the central maxima, let it is y1 dash, which is given by 2n minus 1 lambda capital D upon 2d. Okay, so here y1 dash is given as small d because the first minima is falling at d. So substituting over here, y1 dash as d, and here is 1, 2 into 1 minus 1, 1, lambda into d upon 2d. Capital D is 1000 small d. So d is equal to lambda into 1000 d upon 2d. This d and d cancels out. So this d is equal to 500 lambda is the relation between d and lambda. Okay, draw the energy band diagram for n type and p type. Okay, you have to draw the valence band, above the valence band, conduction band. Okay, and in case of n type, the donor energy level is just below the conduction band. And also the number density of the electrons will be more as compared to the number density of holes. Whereas in p type, the acceptor energy level will be just above the valence band. Okay, how much above? 0.01 electron volt to 0.05 electron volt. And here the number density of the holes will be more. Next question, a PN junction diode is damaged by strong current. Yes, what happens when the strong current flows? It gets heated up. So large number of covalent bonds will be broken and it gets damaged. Impurities are added in intrinsic semiconductors to increase its conductivity. Question number 22, how are infrared waves produced? Okay, they are produced by hot bodies, hot molecules. Okay, also the semiconductor diode, they also emit infrared waves. Why these waves are referred as heat waves? Because the water molecules present in most of the materials, they readily absorb the infrared waves. After absorption, their thermal motion increases, so they heat up the surroundings. Two uses of infrared waves. Infrared lamps, they are used in physical therapy, in greenhouse effect. Infrared detectors are used in Earth satellites, in remote switches of household electronic gadgets like TV, video recorder, etc. Infrared waves are used. How are X-rays produced? They are produced by bombarding a metal target by high energy electrons, a high moving electron stream. When it hits a heavy metal target, X-rays are produced. Any two uses of X-rays? In the diagnostic tool in medicine, treatment for certain forms of cancer, and in the study of crystal structure. Question number 23. Why and how a galvanometer is converted into an emitter? Okay, why it is converted? Because galvanometer is a very sensitive device. It cannot measure the current. Emitter measures the current. And how it is converted? By connecting a shunt resistance, a very low resistance parallel to the galvanometer, it gets converted into emitter. Next question. Question number 24, which is, what is meant by ionization energy? Ionization energy the energy required to remove an electron from ground state to infinity, or to remove an electron from the atom. That energy we call it as the ionization energy. And what is its value for hydrogen atom? It is 13.6 electron volt. Next is define the term mass defect. It is the difference in the mass of the nucleons and the rest mass of the nucleus. Mass of the nucleons, that is the mass of protons plus the mass of neutrons. That is the mass of the nucleons, and the rest mass of the nucleus will be different, slightly different. So this difference between these two masses, we call it as the mass defect. How is it related to the binding energy? We know that binding energy is equal to delta M into C square. Delta M is the mass defect. More the mass defect, more is the binding energy. Okay, more binding energy means more will be the binding energy per nucleon. And binding energy per nucleon represents the stability of the nucleus. So more the mass defect, more will be the binding energy per nucleon, and more stable will be the nucleus. 60 centimeter in front of a concave spherical surface of refractive index 1.5. Radius of curvature is given. Find the position of the image. So which formula here you will use? The refraction through the spherical surfaces when the object is in the rarer medium. Minus N1 upon U plus N2 upon V is equal to N2 minus N1 upon the radius of curvature. Here, substituting the values, N1 is the refractive index of air, which is 1. U here is given as 60 centimeters in front of the concave. That is, U will be minus 60, opposite to the direction of incident light. N2 here is given as 1.5 plus 1.5 upon V, which has to be determined position of the image. N2 minus N1, 1.5 minus 1 is 0.5 upon the radius of curvature. Radius of curvature here will be minus 20, as it is a concave refracting surface. Okay, so the object is in air at a distance 60 centimeters. Okay, so here you have to find out the position of the image, and its radius of curvature will be the towards the left, so it will be taken as negative. So on simplifying, we get V is equal to minus 36 centimeter. Next is section C, 3 marks each. Given that RL circuit, R is given, L is given, V is given in the form of equation, compare it by V is equal to V naught sin omega t. You have to calculate the impedance. Impedance we know is equal to under root R square plus XL square. Okay, so first let's find out XL. XL is equal to omega into L. Omega, comparing by this equation, V is equal to V naught sin omega t. Omega is how much? 100 pi. And L given over here, 100 upon pi, but this is in millihenry. So in order to convert it in Henry, 10 raised to the power minus 3. So this you get it to be 10 ohms. Okay, now Z is equal to under root R square. R is 10, square will be 100, 10 square is 100. XL is also 10. This is also 100. That is under root 200 ohms. Or this can be written as 10 root 2 ohms. So the impedance is 10 root 2 ohms. Now the B part is phase angle. We know that tan phi is equal to XL upon R, where phi is the phase angle. XL is 10 ohm, R is also 10 ohm. So tan phi is equal to 1. So phi is equal to 45 degrees, or you can write it as pi by 4. So the phase angle is pi by 4. Voltage drop across the inductor. That is, you have to find out VL. VL will be equal to IRMS into XL. Now IRMS is VRMS upon Z. Okay, into XL. This is the sign of multiplication into XL. Okay, now VRMS, V naught upon root 2. comparing this equation by with the standard equation, V is equal to V naught sine omega t. So V naught is 141. VRMS will be 141 V naught upon root 2. So this is VRMS. And in the denominator multiplied by Z, Z is how much? 10 root into XL. XL is how much? 10 ohms. Okay, on simplifying it, you get it to be 70.5 volts. So the voltage across the inductor is 70.5 volts. Next question, question number 27. A ray of light is incident on a glass prism of refractive index mu. Okay, and refracting angle is A. It just suffers total internal reflection at the other face. Let's draw the figure. Okay, there are marks for the figure also. So this is the incident light. Let us draw the normal over here. This gets refracted, and on the other face, it is grazing over the surface of this AC. Okay, and angle A is the refractive angle. This is the figure. Okay, now here we know that this is the angle of incidence. This is the angle of reflection. Let us write it by R1. Here, draw the normal on this AC phase. This angle, we take it to be R2. Okay, here, this angle will be equal to 90 degree. Okay, the angle of refraction from the AC phase will be equal to 90 degree. Okay, now we know that R1 plus R2 is equal to angle A. This is R2 angle. Okay, also here R2 is equal to critical angle. R2 is the critical angle because then only here the refracted ray is grazing on the surface. That is the angle of refraction in the other medium is equal to 90 degrees. So R2 here is equal to IC, and we know that angle A is equal to angle R1 plus angle R2. So here R1 angle will be equal to A minus R2 angle, and R2 angle is critical angle of incidence. So here R1 is equal to A minus IC. Okay, now from this surface, from the surface AB, wherever the refraction is taking place, let us find out the refractive index of the second medium, that is of the medium of this prism, material of this prism to air. Mu 21 is equal to sine I upon sine R1. We are using the Snell's law of refraction from the refraction through AB phase. Okay, here sine I, and what is R1 over here? Sine A minus IC is the relation between the angle of incidence, angle of prism, and the critical angle. Okay, so here we have obtained the relation. Next question, question number 28. Distinguish between nuclear fission and fusion. You must have done. Fission means splitting of the heavy nucleus into two smaller nuclei. Fusion means fusion of the two lighter nuclei into a big nucleus, into a big stable nucleus, by giving one example of each. Okay, next is explain the release of energy in the nuclear fission and fusion on the basis of binding energy per nucleon curve. The binding energy per nucleon of the products is greater than that of reactants. Next is how is the size of the nucleus found experimentally? By the method of scattering. Write the relation between the radius and the mass number of the nucleus. We know that R is given by the nuclear radius, R naught empirical constant, mass number raised to the power 1 by 3. This is the relation. R naught is constant. Prove that the density of the nucleus is independent of its mass number. Nuclear density, mass upon volume. Mass of the nucleus will be mass of one nucleon into the total number of nucleons. Total number of nucleons is the mass number upon the volume of the nucleus, as it's a sphere, 4 by 3 pi r cube. Okay, substituting this radius to be R naught, A raised to the power 1 by 3, we get R naught cube A raised to the power 1 by 3 into 3. This will be A. A and A cancels out. Hence, the nuclear density is independent of the mass number. Next question, question number 29. Two cells of EMF E1, E2 and their internal resistance R1, R2 are connected in parallel. Okay, let these are the two cells R1, R2, and the current from the first cell, let it be I1, from the second cell I2. So here I is equal to I1 plus I2. Okay, a simple derivation, and here you have to find out the expression for the equivalent EMF. The equivalent EMF will be equal to E1 R2 plus E2 R1 upon R1 plus R2. Okay, this is a very simple derivation. Next is two charged conducting spheres of radii A and B are connected to each other by a wire. Find the ratio of the electric field. Okay, whenever two conductors are connected by a conducting wire, then the potential becomes the same. So the potential of the first sphere will be equal to the potential of the other sphere, potential KQ by R. So first sphere, let it is having a charge Q1, Q1 upon A, K, Q2 upon B. So from here, Q1 upon Q2 is equal to A upon B. Okay, now here you have to find out the ratio of the electric fields. E1 is KQ by R square, KQ1 upon A square upon E2. E2 is KQ2 upon B square. So this is equal to Q1 upon Q2 into B square upon A square. From here, Q1 upon Q2 is A upon B. So the ratio of the electric fields will be equal to B by A. There's a choice over here. Two capacitors connected by a conducting wire. So the potential becomes the same. The charges flow from the higher potential capacitor to the lower potential till the potential becomes the same. Here you have to find out the final charges on A and B. Q is equal to C into V. The first capacitor has a capacitance C and it is charged to V voltage. Okay, both of them reach to the same potential. QB will be equal to, its capacitance is 2C and this also reaches to the same potential, common potential, what we call it. So QA to QB is equal to 1:2. Now the total electrostatic energy stored in A and B finally, that too stored in A initially. Okay, initially the energy stored in the first capacitor is half C1 V square. C1 here is equal to C and it is charged to V. So half CV square. Okay, now the final energy stored will be the final energy stored in the first capacitor plus the final energy stored in the second capacitor. Okay, and the final energy stored will be equal to half C1 V1 square plus half C2 V2 square. Okay, here V1 will be equal to V2, that is both of them reach to the common potential. So we'll find out the common potential. C1 is C and C2 is equal to 2C. So first let's find out the common potential. Common potential is given by C1 V1 plus C2 V2 upon C1 plus C2. Here C1 is C, V1 is V, V2 is 0 because it is uncharged. C plus 2C, this is equal to 3C. So the common potential is V by 3. Now here V1 and V2 both will be equal to V by 3 because they reach at the common potential. So the final energy stored will be equal to half C1 here is C V1 square V square upon 9 plus half C2. C2 here is 2C. Again V2 is V square upon 9. Okay, on simplifying it, we get half CV square upon 9. You can take it common. 1 plus 2, that is 3. So we get half CV square upon 9 into 3. So half CV square upon 3. Now here you have to find out the ratio of the final energy to that of initial energy. Okay, ratio of the final energy to the initial energy. So what do you get? 1:3. So what is the ratio? It is 1:3. There are 3 questions over here. Question number 31, Huygens state Huygens principle, and with the help of diagram, show how a plane wave is reflected from a surface and verify the laws of reflection. Okay, this is a very simple question you must have done. A concave mirror of focal length 12 centimeter forms a 3 times magnified virtual image of an object. Find the distance of the object from the mirror. Okay, as it's a concave mirror, so the mirror formula is 1 upon f is equal to 1 upon b plus 1 by u. Your focal length is minus 12 centimeter as it's a concave mirror, and magnification we know is given as 3, and magnification for a mirror is minus v by u. So from here v is equal to minus 3u. So substituting it over here and finding out u, you get to be minus 8 centimeters. The choice part is draw label diagram for refracting telescope. Okay, very simple. Define its magnifying power and 2 limitations of the refracting telescope over a reflecting telescope. Okay, refracting telescope, it has spherical aberration because the objective is a lens, convex lens of large aperture. So the spherical aberration, chromatic aberration arises. Also, the image is not as bright as that in case of a reflecting telescope. Second part is the focal length of the objective and the eyepiece of a compound microscope are given as 1 and 2.5 centimeter respectively. Find the tube length for obtaining the magnification of 300. We know that the magnifying power or the magnification is equal to L upon FO into D by FE when the final image is formed at infinity. All these values are given. We have to find out L. Substituting the values, magnifying power is 300. L has to be determined. FO is 1. Least distance of distinct vision 25 centimeters. And FE is given as 2.5. On simplifying it, you get the length to be 30 centimeter. So the length of the tube is 30 centimeter. Next question, question number 32. Using Gauss law, find the expression for the electric field due to a long, thin, straight wire having a linear charge density lambda. This is a very simple derivation which comes out to be E is equal to lambda upon 2 pi epsilon naught into R. An infinitely long positive charge state wire has a linear charge density and electron is revolving in a circle with a constant speed v. Okay, so this is a thin charged wire and an electron is revolving around it with a velocity v. Okay, now the necessary force is centripetal force, which is equal to the force on this electron, and the force on the electron is equal to E into E, Q into E. So Q here is the charge on the electron, E into E, and capital E is the electric field due to this line charge. Substituting the electric field to be lambda upon 2 pi epsilon naught into R. R and R cancels out. So we get this expression. Now here you have to find out the kinetic energy. To get the kinetic energy, let us multiply both sides by half, because we know that kinetic energy is half mv square. E lambda upon 4 pi epsilon naught is the expression for the kinetic energy. C part, draw the kinetic energy as a function of lambda. As from this equation, we see that kinetic energy is directly proportional to lambda. So the graph will be a straight line passing through the origin. The choice question is two identical point charges, if one is Q, the other is also Q, are situated at 0, 0 and A0. Is there a point on the line joining at which the electric field is 0? If we find the electric field at the midpoint, the electric field due to this Q charge will be E1, pointing away from this, pointing along this direction. Whereas due to this Q charge, the electric field at the midpoint will be E2, pointing in the opposite direction. The magnitude of E1 and E2 is same and the direction is opposite. So at the midpoint, the net electric field will be 0. Is there a point on the line joining at which the electric potential is 0? Potential cannot be 0. Why? Because it's a scalar quantity. Here, if you find out the potential due to these two charges will be added up. As electric field is a vector quantity, so the resultant electric field at the midpoint will be 0. But the potential at any point can never be equal to 0. Second part is state the significance of negative value of the electrostatic potential energy. Negative value of the electrostatic potential energy means the charges are bound together, or you may say the forces are attractive in nature. There's one numerical along with it. Okay, at the vertices of an equilateral triangle, there are three charges, and here you have to find out the potential energy of this system. Potential energy will be equal to, we know that the expression of the potential energy is kq1 q2 upon r. Between these two charges, there will be some potential energy, k q1 into q2, 4 into minus 4, minus 16 upon the distance is 2 meters. Okay, as it's an equilateral triangle, each side is 2 meters. Okay, now this is not minus 16, 4 microcoulomb into minus 4 microcoulomb. Micro is 10 raised to the power minus 6 into 10 raised to the power minus 12, which will multiply outside the bracket. Between these two charges also there will be some potential energy. How much is it? 4 into minus 2, minus 8 upon 2. Between these two charges, 4 into 2 plus 8 upon 2 into 10 raised to the power minus 12. Micro into micro, 10 raised to the power minus 12. This cancels out. K, the value of K is 9 into 10 raised to the power 9 into minus 8 into 10 raised to the power minus 12. Okay, on simplifying it, get it to be minus 7.2 into 10 raised to the power minus 2 joules is the answer. Coefficient of self-induction, which is defined as magnetic flux per unit current, or it can also be defined as induced EMF produced upon di by dt. Obtain an expression for the self-inductance for a long solenoid. It's given by, this is a simple derivation, mu naught n square A upon L. This is the expression. Next is calculate the self-inductance from these tables. Okay. Now, one table is for the AC source and the other is for the DC source. So from the AC source, you can find out Z, and from the DC source, you can find out R. Okay, so Z here is equal to V upon I from the AC source, 3 upon 0.5 or 6 upon 1. What do you get? 6 ohms. From the DC source, you will get the resistance. Resistance is equal to V upon I, 4 upon 1 or 6 upon 1.5. You get it to be 4 ohms. Now we know that as it is an LR circuit, Z is equal to under root R square plus XL square, or we can write it as Z square is equal to R square plus XL square. So XL square will be equal to Z square minus R square. Okay, that is Z square 36, R square will be 16. So XL square is 20, that is XL will be equal to under root 20 ohms. Okay, now here you have to find out the inductance. We know that XL is equal to 2 pi nu into L is equal to under root 20. So L will be equal to under root 20 upon 2 pi into nu, and here the nu given is nu is equal to 200 upon pi, 200 upon pi under root 20 upon 400, because this pi and pi cancels out. Okay, this much Henry. The choice part is, with the help of label diagram, describe the principle and working of an AC generator. Principle is electromagnetic induction, and working, you have to draw the diagram and then explain it. And obtain the expression for the instantaneous value. Instantaneous value is E naught sine omega t, where E naught is the peak value, which is equal to N into B into omega, NBA omega. This is a very simple derivation. Based on it, there is a numerical in the second part. Okay, here you have to find out the maximum EMF generated. Maximum EMF generated, NBA omega. All these values are given. N is 100. Magnetic field is 0.8. And the area is 0.5 meters square into omega is 60 radian per second. So on simplifying it, you get the answer to be 2400 volts. So the peak value of the induced EMF will be 2400 volts. Okay, also power dissipated is to be found. Power dissipated will be equal to ERMS square upon R. Okay, this is E naught. ERMS square will be equal to E naught upon root 2. 2400 into 2400 upon root 2 square will be 2. And the resistance is given as 100 ohm. Okay, and on simplifying it, you get it to be 28.8 kilowatt is the answer. Now the next are two case-based study questions. The first one from the figure, you have to find out which beam of light has highest frequency. Okay, the one which is having the highest stopping potential. Stopping potential is the retarding potential to bring the photoelectric current to be 0. Okay, so which beam? The one which is having highest potential, that is B. Which beam has the longest group wavelength? The one which is having the lowest stopping potential, that is C. Which beam ejects photoelectrons with maximum momentum and Y? Okay, for maximum, we know that E is equal to h nu. So which beam will have the maximum momentum? The one which is having the maximum kinetic energy. And maximum kinetic energy, the one which is having the maximum frequency. Which one is having the maximum frequency? B. So B beam will have max. Next is, what is the effect on threshold frequency and stopping potential on increasing the frequency of incident light? Threshold frequency depends upon the metal. So it is not dependent upon the frequency of the incident wave. On increasing the incident frequency, threshold frequency remains the same. But the stopping potential changes. Why? Because according to the Einstein's photoelectric equation, we know that half mv maximum square, that is the maximum kinetic energy, is equal to h nu minus h nu naught. Okay, and this half mv maximum square can be written as E into V naught. Okay, so on increasing the frequency, the stopping potential also increases. Okay, next 35, question number 35 is, explain the reason of jumping of the ring when the switch is closed. Okay, so when the switch is closed, the induced current will be produced, so the ring jumps. What will happen if the terminals of the battery are reversed and then the switch is closed? Then the direction of the current is reversed, but still the induced current will produce and the ring will again jump. Explain the two laws that help us to understand this phenomena. The two laws are Faraday's laws of electromagnetic induction, which states that whenever there is a change in magnetic flux linked with a coil, an induced EMF or the current is produced. And the second is Lenz's law, which states that the induced EMF is produced, which opposes the rate of change of magnetic flux. Okay, again, there is a choice over here. The choice part is briefly explain the various ways to increase the strength of the magnetic field produced inside a long solenoid. We know that magnetic field produced inside a long solenoid is given by mu naught N into I upon L. To increase, what can be done? The number of turns can be increased, current can be increased, length of the solenoid can be decreased, or the soft iron core can be introduced inside the solenoid so that the permeability increases and hence the magnetic field can be increased. Hope it's all clear. You understood the paper very well. Thanks for watching. Thank you.